What is the multiverse hypotheses? What is the holographic multiverse? What is the simulated multiverse? What is the multiverse hypotheses? Multiverse hypotheses are speculative theories in the field of cosmology and theoretical physics that propose the existence of multiple universes beyond our observable universe. These hypotheses suggest that our universe is just one of many universes that could exist, each potentially having different physical properties, constants, and laws of physics. It's important to note that these hypotheses are still a topic of ongoing research, debate, and speculation, and there is currently no direct observational evidence supporting the existence of multiverse. Here are a few different multiverse hypotheses that have been proposed. Bubble multiverse, eternal inflation. The bubble multiverse hypothesis, also known as the theory of eternal inflation, is a speculative concept in cosmology that arises from the theory of cosmic inflation. Cosmic inflation is a theoretical framework that suggests the universe underwent a rapid and exponential expansion in its early moments, smoothing out its overall structure and leading to the large-scale uniformity we observe today. The bubble multiverse hypothesis proposes that this inflationary process did not cease everywhere at the same time. Instead, different regions of space could have stopped inflating at different times, giving rise to bubble universes within a larger, continuously inflating space. Each bubble universe is like a separate pocket of space-time, with its own physical properties, constants, and laws of physics. Here's a basic outline of how the bubble multiverse hypothesis works. Inflation begins. In the very early moments of the universe, a period of rapid inflation occurs, causing the universe to expand exponentially. Inflationary epochs. Within this inflationary universe, there are regions where inflation ends earlier than others due to quantum fluctuations. These regions become pockets where inflation has ceased, and they are separate from the still inflating regions. Bubble universes. Each pocket where inflation has ended becomes a separate bubble universe. These bubble universes can have different physical properties and constants because the conditions for each bubble's formation might be slightly different. Observable universe. Our observable universe is just one of these bubble universes. The inflationary process has ceased within our bubble, allowing it to cool and evolve into the universe we observe today. The bubble multiverse hypothesis has been proposed as a possible explanation for some of the observed features of our universe, such as the apparent fine-tuning of physical constants and the uniformity of the cosmic microwave background radiation. It's important to note that while this hypothesis is intriguing and offers a potential solution to certain cosmological puzzles, it remains highly speculative and has not been confirmed through direct observation or experimentation. Research into the bubble multiverse hypothesis involves complex mathematical and theoretical work, often within the framework of inflationary cosmology and string theory. It's worth emphasizing that the concept of a bubble multiverse is just one of several speculative ideas within the broader context of multiverse hypotheses, and scientists continue to explore these ideas to gain a deeper understanding of the fundamental nature of our universe. Many worlds interpretation of quantum mechanics. The many worlds interpretation, MDI, is a controversial interpretation of quantum mechanics that suggests that every possible outcome of a quantum event actually occurs, giving rise to a branching or splitting of the universe into multiple parallel universes. In other words, every time a quantum system undergoes a measurement or interaction, the universe as a whole splits into multiple branches, each corresponding to a different outcome of that event. This interpretation was first proposed by physicist Hugh Everett II in 1957. The many worlds interpretation. Superposition and quantum measurement. According to MWI, when a quantum system is in a superposition of multiple states, all of those states exist simultaneously in different branches of the universe. When a measurement is made, rather than collapsing to a single state, the universe branches into multiple versions, one for each possible outcome. Branching and splitting. Every time a quantum event occurs, the universe splits into multiple branches, each representing a different possible outcome. These branches evolve independently from that point onward. Quantum probability. In the many worlds interpretation, probabilities arise due to the relative frequency of outcomes in different branches. The probability of observing a particular outcome is related to the fraction of branches in which that outcome occurs. Observer's role. MWI proposes that observers are also part of the quantum system, and their perceptions are determined by the branches of the universe to which they become correlated. Each observer perceives a single outcome of a measurement, but other versions of the observer perceive other outcomes in different branches. Critiques and controversies. The many worlds interpretation is not without its criticisms and challenges. No direct evidence. As of now, there is no direct experimental evidence for the existence of parallel universes or the branching of the universe as described by MBI. The interpretation is often criticized for lacking empirical testability. Complexity in Occam's razor. MBI introduces an immense number of parallel universes, each with its own version of events. Some critics argue that this introduces unnecessary complexity and violates the principle of Occam's razor, which suggests that simpler explanations are preferred. Observer problem. The role of the observer and the process of measurement in MDI remain unclear and raise questions about how observers become correlated with specific branches. Quantum non-locality. MDI doesn't provide a clear explanation for quantum non-locality, the phenomenon where entangled particles seem to instantaneously influence each other's states across large distances. Interpretational freedom. Quantum mechanics allows for multiple valid interpretations, and MDI is just one among several. Other interpretations, like the Copenhagen interpretation, pilot wave theory, and objective collapse models, offer alternative ways of understanding quantum behavior. Brain cosmology. Brain cosmology is a theoretical framework that extends ideas from string theory to cosmological scenarios. It proposes that our observable universe is a three-dimensional brain, short for membrane, embedded in a higher dimensional space, which is sometimes referred to as the bulk. This concept is part of the broader context of string theory, a theoretical framework that aims to unify the fundamental forces of nature and describe the behavior of particles as tiny, vibrating strings. In brain cosmology, our universe is considered to be a brain floating in a higher dimensional space. This theory offers a way to address certain questions and challenges in cosmology, such as the nature of gravity, the origin of the universe, and the potential existence of other universes. Here are some key points and implications of brain cosmology. Extra dimensions. Brain cosmology posits the existence of extra dimensions beyond the familiar three dimensions of space and one dimension of time. These extra dimensions can be compactified or curled up at a very small scale, making them difficult to observe at our current level of technology. Gravity in higher dimensions. In brain cosmology, the force of gravity can leak into the extra dimensions. This can lead to modifications of gravity's behavior on cosmological scales and provide explanations for some observed phenomena, such as the weakness of gravity compared to other fundamental forces. Hierarchy problem. Brain cosmology offers a potential solution to the hierarchy problem, which concerns the vast difference in scales between the strengths of different forces in nature. The hierarchy problem is related to why gravity is much weaker than other forces. The presence of extra dimensions in brain cosmology could provide an explanation for this disparity. Cosmic inflation. The concept of brains and extra dimensions has been used to provide a framework for understanding cosmic inflation, a period of rapid exponential expansion in the early universe. Inflation could be triggered by the motion of brains in the higher dimensional bulk. Multiverse hypotheses. Brain cosmology has been invoked in some models of the multiverse, suggesting that our universe is one of many brains floating in the higher dimensional space. These brains could have different properties and physical laws, leading to the possibility of a multiverse. Parallel universes. The concept of parallel universes, also known as a multiverse, is a speculative idea in cosmology and theoretical physics that suggests the existence of multiple universes beyond our own. These parallel universes could have different physical properties, constants, and even different laws of physics. The idea of parallel universes has captured the imagination of scientists, philosophers, and science fiction writers, but it's important to note that this concept is still largely theoretical and has not been empirically proven or observed. Holographic multiverse. The holographic multiverse is a speculative hypothesis that suggests the existence of multiple universes, each of which is a projection or hologram from a higher dimensional boundary. This idea is inspired by concepts from string theory, black hole physics, and the holographic principle, which is a concept that originated from attempts to reconcile general relativity with quantum mechanics. The holographic principle posits that the information contained within a given volume of space can be fully described by the information on the boundary of that volume. In other words, the universe could be thought of as a hologram, with all its features and dynamics encoded on a two-dimensional surface. This principle has been explored in the context of black hole physics and quantum gravity, and it has led to insights into the nature of entropy, information, and the fundamental structure of space-time. The holographic multiverse hypothesis takes this idea a step further and proposes that different universes could be projections from a shared higher dimensional boundary. Each universe could correspond to a different arrangement of matter, energy, and physical laws on this boundary, resulting in distinct holographic projections that we perceive as separate universes. The holographic multiverse hypothesis include shared information. According to this hypothesis, the information for multiple universes is encoded on a common boundary. This could allow for a mechanism through which different universes are interconnected in some way. Diverse universes. Each universe projection could have its own unique set of physical laws, constants, and properties. This could explain the observed diversity of physical phenomena and constants in our universe. Higher dimensional physics. The holographic multiverse draws on ideas from higher dimensional physics and string theory, suggesting that the true nature of reality may extend beyond our familiar 3 dimensions of space and 1 dimension of time. Challenges and open questions. While the holographic principle has been a fruitful area of theoretical research and has provided insights into fundamental physics, its application to the multiverse hypothesis remains speculative and faces challenges. It is not currently clear how such a holographic projection mechanism would work in practice or how it could be tested through observation or experiment. Simulated multiverse. The concept of a simulated multiverse is a speculative idea that suggests our universe, and possibly other universes, could be part of a simulated reality created by an advanced civilization, superintelligent beings, or some form of higher dimensional entity. This idea is influenced by developments in computing, virtual reality, and theoretical physics, and it has gained attention in both scientific and philosophical discussions. Simulation hypothesis. The simulation hypothesis proposes that our entire reality, including the universe and everything within it, could be a highly advanced computer simulation. This concept draws parallels with the way humans create virtual worlds and simulations in video games and simulations. Advanced civilization. In the context of a simulated multiverse, the creators of the simulation could be an incredibly advanced civilization capable of simulating entire universes. This could be done for various purposes, such as scientific exploration, entertainment, or to understand the origins of their own universe. Nested simulations. The concept of a simulated multiverse could extend to the idea of nested simulations, where simulations within simulations could create a hierarchy of universes or realities. Each level of simulation could have its own set of physical laws and properties. Observable effects. In some versions of the simulation hypothesis, researchers speculate that there might be subtle clues or glitches in the simulated reality that could potentially be detected by advanced beings within the simulation. These could include anomalies in cosmic background radiation, limits on the precision of physical constants, or unusual patterns in the behavior of particles. Philosophical implications. The simulated multiverse raises profound philosophical questions about the nature of reality, consciousness, free will, and the relationship between creators and their creations. Scientific challenges. While the concept is intriguing, it currently lacks empirical evidence and faces scientific challenges. It's not clear how one could definitively prove or disprove the idea of a simulated multiverse, and it's uncertain if our current understanding of physics and computation is sufficient to fully explore this hypothesis. Ethical and moral considerations. The simulated multiverse hypothesis also raises ethical and moral questions, such as the implications of creating simulated beings with consciousness and the responsibilities of the creators toward their simulated inhabitants. It's important to emphasize that these multiverse hypotheses are highly speculative and often arise from attempts to reconcile various challenges and questions in cosmology and theoretical physics, such as the fine-tuning of physical constants, the nature of dark energy, and the behavior of quantum systems. While these ideas are intriguing and have generated much interest and discussion, they currently lack empirical evidence and remain theoretical concepts that continue to be explored and debated within the scientific community. That's all in this video. If you like the information, please hit like and subscribe to this channel, and be connected to this channel for more space information.